Hello. This lecture is part 3 of section 1.3 from Math 311, a linear algebra course at Western Illinois University. So we've defined lines and we've talked about planes. Now we're going to show just a few of the geometric applications of them. We've already talked about 3 of them. And we'll review these, but we're going to see that we're really going to be looking at how do we measure distances, like the distance between a point in a line, or a point in a plane, or the distance between 2 planes, so on, stuff like that. And we're going to see that really there are formulas that you can find in books, but we're going to see. I want to show you that these can all be derived from just some simple principles about vectors. And in particular, the ones up here. This is really all we really need. I just remind you that the length of a vector, and this, by the way, this holds in any dimension. These vectors could be in any dimension. The length of the vector v is the square of the length of v is going to be the dot product of v with itself. Then we have this projection of v onto a vector u. Remember, this vector v can be written as the sum of 2 vectors, one of which is parallel to u, and the other which is orthogonal to u. And we said that this is the projection of u. It's a multiple of u, and it's defined by this formula. And then the orthogonal vector is just v minus the projection. Okay, that's going to play a big role in all of these. So if you know this, in a sense, this is all you really need to know. And then, of course, we know how to measure the angle of 2 vectors by computing this using finding the cosine first. Okay, so we've already talked about, in the previous video, we talked about the distance between a point and a line. Okay, and in all of this, we're going to see that a picture is worth 1,000 words. Okay, we're going to try to get you the principle with as little notation as possible, right? So the distance between a point and a line, well, all you really need to do is find a point on that line, and then consider the vector connecting these 2 points. And then we saw that the projection, rather the distance that we're looking at, this distance, which can be thought of as this. If we remember, we compute if this vector is v, and this the direction vector of the line is d, then this distance right here is the projection of v onto d. Okay, so the distance in this case is the length of this difference, v minus the projection of v onto d. Okay, we talked about that. And then we can use a similar principle. We use a similar principle for the distance of 2 parallel lines. We just have to find 2 lines, 1 point on each line. And since they both have the same direction vector d, okay, we can just consider the vector connecting these 2. And once again, this distance is going to be v minus the projection of v onto d. Okay, we talked about this. Basically, it's the same idea. We're just finding a point. Finding 2 points on a point on each line. And then, of course, we also talked about the angle between 2 intersecting lines. If the direction of this line is d1 and this direction is d2, then the cosine of the angle is d1 dot d2 divided by the length of d1 times the length of d2. Okay, so we talked all about this before. Now, the next idea we want to talk about is the distance between a point and a line. And in this case, we can once again we can start with a vector connecting this given point to any point on the plane. We really only need one point in this plane. Okay, and then we connect these 2 points with a vector. Once again, we can call it v, and we're trying to find this distance here. All right, now this, rather than try to project, in this case we want to project v onto a vector that's perpendicular to the plane, because we can't, because there are just so many vectors that are embedded in the plane, right? So we actually want to project it. Remember, the normal vector n is orthogonal to this, right? So we can actually project v onto this vector n. And when we do that, we'll actually, the projection will be here. But this distance and this distance are going to be the same. Okay? So we can see that the distance in question here will be the length of, we don't have to subtract, we don't have to subtract anything, right? Because the the normal vectors right here. So this is just going to be the length of projection of v onto n. Okay, which, and I will say that we know the projection can be calculated as v dot n divided by n dot n, okay, times n. Okay, but remember, this is just a scalar. This is a real number, so this might be positive or negative. So we can actually just get away that the length of this vector is really just going to be the length of the absolute value of this number times the length of n. So we can get away by just computing the absolute value of v dot n divided by the n dot n times the length of n. Okay. So for this example, we're going to use the same plane in all these examples today. We're going to consider the plane x given by x plus y minus 2z equals 4. And in this example, we want to find the distance between the shortest distance between this plane and this point. Okay, so what we can do is we first we can first find we'll first note what the norm vector is. It's going to be the coefficients here are 1, 1, negative 2. Okay, now we need a v. And we have the point 1, 2, 3 here, and then we have our plane, and we just want to pick a particular point on the plane. Now there are lots of ways to find a point, and the thing here is you can basically find it by setting all but one of the variables equal to 0. And what I'm going to do, if I plug in 0 for y and z, then I get x has to be 4. So the point 4, 0, 0 is in this plane, right? And then we can find the vector v, which will be 1 minus 4, that's negative 3. 2 minus 0 is 2. 3 minus 0 is 3. All right? And then, okay, so n dot v is going to be negative 3 plus 2 minus 6. That should be negative 7. And then n dot n, dot product of n with itself, is 1 squared plus 1 squared plus 2 squared. That's 6. Okay? So the distance is going to be the absolute value of negative 7/6 times the length of v, or rather the length of n, which is the square root of 1 squared plus 1 squared plus negative 2 squared. So this will be 7/6 times the square root of 6. Or you can leave it like that, or you can right? In this not so nice form of 7 divided by square root of 6, okay? And then you can plug it in your calculator, okay? Which, if you want it to. All right, now let me just, before going on to this, the next example, let me just say that in your calculus book and also in your linear algebra book, they give you a more explicit form for the formula for this distance. But I just want to show you kind of where this came from. So in the formulas in your calculus book, they say, well, if you already know a point in the plane, let's say x1, y1, z1, and x0, y0, z0 is the point off the plane you're trying to find this distance from. Once again, you can let v be this. And if our equation is given by ax plus by plus cz equals d, if this is the equation of the plane, then notice that if this point is in the plane, we get ax1 plus by1 plus cz1 equals d. So, like in this case, v now is going to be x0 minus x1, y0 minus y1, z0 minus z1, n will be abc, and then v dot n, basically we can use this to derive the formula. V dot n will be a times x0 minus x1 plus b times y0 minus y1 plus c times z0 minus z1. And if we distribute everything and collect like terms, this becomes ax0 plus by0 plus cz0 minus ax1 minus by1 minus cz1, but that's just d. So we get minus d. Okay, and that's how you can fill in the details now, but that's where this expression comes. So you take the absolute value of this, divide by something, and multiply by something, and you get the formula. That's it. That's in your textbooks. Okay, so that's where this. So really, everything comes from this idea, this principle. All right. Next, I want to take a little detour here and just clarify a couple things about lines and planes. Well, how they intersect. Okay, so a line may intersect a plane. It may not. If it does intersect it, it'll either intersect it at a point, or it might be embedded in the plane. Okay, or if it doesn't, well, if it doesn't, I think it should be clear that the line has to be somehow parallel to the plane, and that would mean that it would have to be orthogonal to the normal vector. Now, that intuitively that should be that kind of makes sense, but let's just prove this mathematically. So let me just state the fact that a line with direction vector d and a plane with normal vector n intersect if and only if, I guess if and only if, either d dot n is not 0 or the line is embedded in the plane. Okay. Now we can see this mathematically a little bit, because we know that every line has a parametric version. Okay, it can be given by these parametric equations, and we know this is the general form of a plane, right? And so how do we do this? How do we find where they intersect? Well, we do some substitutions, right? If x, y, z is in this point of intersection, then this holds, but x, y, z are also equal to these expressions, so we can substitute these in here. And then if I skipped a couple steps, but we can multiply everything out, put some stuff on the other side, factor some stuff out, and what we get is big A plus big B plus big C little c times this parameter t is equal to a constant over here, which is already given, right? Because the x0, y0, z0s are constants, right? So we have something times t equals a constant, and that something is in fact the dot product, right? Because in this case the normal vector is AB, capital A, B, C, and the direction vector is little a, little b, little c. Okay, so this boils down to the dot product times t is equal to this constant, right? And so what happens here, now there's two cases. Either if this is not zero, if it's not zero, then we can divide by whatever this number is, and we get t equals some number, and that's the only value that t that works, right? So we get one point of intersection. Now, if this is zero, then this is zero, which would mean that ax0 minus by0 plus c0 is equal to d. Okay, and if that's the case, that means that this point is also going to be in the plane. Okay, which means everything would have to be in the plane, right? Because and also if this is zero, then this equation holds. So it doesn't matter what t is. So any value of t in that case would give you a point in the plane. So that's why if this is zero, then we get it's well, there I should say. Let me back up and say this. If we know that if x0, y0, z0 is not in the plane, then this is not zero. If this is not zero, then there's no way that this can be zero, right? If this is zero, and this is zero, any value of t works. So that means that the entire line is embedded in the plane. Okay. So basically, again, that's why that if this dot product is zero, that is, if d and n are orthogonal, then that means that there's no intersection, or the line is embedded in the plane. Okay, let's see what happens in these two examples here. And here I'm just going to try to find a point of intersection if possible. Okay, so in example 2, we can see that in this case the direction, what's the direction? 3, negative 1, 5. Okay, and in this case our normal vector is going to be 1, 1, negative 2. Okay. Let's just check that this works. D dot n, that would be 3 times 1 plus negative 1 times 1 plus or minus 10. Okay, that is going to be minus 8, right, which is not 0. Okay. All right. So that means that there's exactly one point of intersection on the plane, and to find out what this is, we can just substitute that in here. So we get that this is 3, or rather 1 times 2 plus 3t, plus 1 times 1 minus t, minus 2 times 5t equals 4. All right, and then this what does this give us? This gives us 2 plus 3t plus 1 minus t minus 10t equals 4. This I believe is going to be the 3 minus 1 is 2. 2 minus 10 is minus 8, so it's minus 8t equals 4 minus 2 minus 1, right? And so this is going to be minus 8t equals 1, so t equals negative 1/8. All right, and then so our point of intersection will be x is given by, now we use these equations here, 2 plus 3 times negative 1/8. Y is going to be 1 minus negative 1/8, and z will be 5 times negative 1/8. So doing a little arithmetic, this is going to be 16 eighths minus 3 eighths. That's 13 eighths. This will be 9 eighths, and this will be negative 5 eighths. And so our point is 13 eighths, negative 9 eighths, or I'm sorry, positive 9 eighths, and negative 5 eighths. And if you do the plug this into this equation, that does work. Okay. Now in example 3, we don't have to do too much because we're going to see that there is no point of intersection. In this case, the direction vector is just given by 1, 1, 1, since that's the coefficients here, right? So direction vector is 1, 1, 1. The normal vector is still 1, 1, negative 2. All right. You can see the dot product is 0. The dot product is 0, and we can see that this line is not embedded in the plane because 2, 1, negative 1, 2, 1, and negative 1 is not in the plane, right? So in this case, the line and the plane don't intersect. All right, so now we know the story in both cases. Let's see what we can do. In one case, if they don't intersect, we can find the distance between them. In the other case, if they do intersect, we'd like to find the angle of intersection. So that's the next page. All right. So the distance between a line and a plane, again, in the case where there's no intersection, and again, we're talking about the shortest distance. So the way we do this, once again, we just need to find a point on the plane, a point on the line, draw the vector connecting them, and then we're going to use the projection as our distance. So this is, if the normal vector is n, and this is v, once again, the distance will be the length of the projection of v onto n. All right, so in this case, in this example, we're going back. We're looking at the case we just looked at, where n, of course, the normal vector of the plane is 1, 1, negative 2. Okay, and okay, now we just need to find a point on the line. The most obvious point on the line we use is 2, 1, negative 1. And we get that by plugging t equals 0 in here. And then we want to find a point on the plane, and we already know that 4, 0, 0 works. That's on the plane. So this is our v here. So v is going to be 2 minus 4. That's negative 2. 1 minus 0 is 1. And negative 1 minus 0 is negative 1. Okay. All right, so we want to find the projection. So v dot n is going to be 1 times negative 2 plus 1 times 1 plus negative 2 times negative 1. Okay, which should be 1, right? Negative 2 plus 1 plus 2. Okay, that's 1. And then n dot n, we should know by now, is 6. Okay, so the projection, so we just take 1/6, the absolute value of 1/6 times the length of n. So this will be 1/6 times, now the length of n is the square root of 6. So we can just write this as the square root of 6 over 6. Okay, or 1 over square root of 6 if you want to do it that way. All right, so that's we get the distance that way. Now in our other case where we had a line that intersected the plane, that in this case, the way we do this is we know that we know that the normal vector and the direction vector almost give us what we want. Okay, here's D and here's N. And we can think about what the angle here is. The actual angle we want is this angle. That's our theta. So we can call this maybe phi. But the thing here is that we can add or subtract 90 degrees to it if we need to. If phi is acute, then we can just subtract this from 90 and get this. And then if we get something that's between 90 and 180, okay, we can subtract subtract something and get that angle. So in number 6 we have let's first find again the normal vector is 1, 1, negative 2, and D. Well, I should say D here is going to be 3, negative 1, 5. Okay, and actually, I guess I should write that down here. But I won't. And then from here we have that the cosine of phi is going to be n dot d, or n, the length of n times the length of d. So what will this be? This is going to be 3 minus 1 minus 10. Okay, right, which is, let me just take a look here. Okay. And then the length of n, we know that's square root of 6, and then the length of d, this is going to be the square root of 9 plus 1 plus 25, so that's 35. Okay. So this is going to be, I believe, 3 minus 11 is minus 8 over the square root of 6 times the square root of 35. Okay, and that's when you do your calculator, and I should have worked this out ahead of time. Okay, because I made a mistake in my notes here. So oops. Okay, well, let's see. You've probably already done this before I did. 0.5520, that's the cosine. Now we take the inverse cosine of that. And we get 123 degrees. Okay, so that would take us way over here, and then okay, and then we can subtract 90 from that. So 123 minus 90. Or actually, yeah, it's 33. Okay. That's the angle between a line and the plane. in this case. Last one here. Another fact that you should keep in mind about two planes. Okay, so if two planes, the most obvious thing is that if two planes have parallel normal vectors, then they're parallel. So if planes P1 and P2 have normal vectors N1 and N2, and the normal vectors are parallel, and again that means that one is a scalar multiple of the other, then either the planes are equal or the two planes do not intersect. And the reason here is given here. You have if these are the equations of the two planes, and the normal vector, the second normal vector is lambda times the first normal vector, where lambda is any real number, we can do a substitution, and then this second equation becomes this, and we could divide everything by lambda. As long as, if lambda is 0, then the normal vectors are both 0, and there's nothing really to talk about. So we can divide both sides by lambda, and then we get this, a1x plus b1y plus c1z is equal to this. Well, we already know that this is d1. Okay, so d1 has to be equal to this. So that means that that d2 is a multiple of d1, in which case this equation is really just this equation just multiplied by a non-zero constant. And of course that, when you multiply by a non-zero constant, you don't really change anything. So these determine the same planes. Okay. All right. Okay. So as long as that we know that they're different, look, if parallel normal vectors and the planes are different, we can talk about the distance between two parallel planes. And once again, we can start by just taking one point in the first plane, 1 point in the second plane, and drawing the vector connecting them. Calling this v, and then we want to find this distance. And remember, both of these have the same, basically, we can take the normal vector n to be the normal vector of both of these if they're parallel. And so the distance will once again be the length of the projection of v onto n. Okay. So in this example, if we wanted to find the distance between these planes, here's our plane that we've been using, and we have another plane given by x plus y minus 2z equals 1. You might think that the distance between them is 3, but that's not quite true. Because there might be two particular points, or one on that are 3 units apart, but that's not the shortest distance. So what would be the shortest distance? Well, we just use this. Okay, so in this case, first let's get 2 points on here. We already know that 4, 0, 0 is a point on this plane, and I think you can see if you let y and z be 0, then x equals 1. It gives us a solution. So this is a point on the second plane. So we can take v will be 3, 0, 0. Okay, n is still 1, 1, negative 2. And then in this case, v dot n, I think you can see, is going to be 3. N dot n is 6. Okay, 3 divided by 6 is 1/2. So the length is 1/2 times the length of v, which we know is the square root of 6. Okay, so that's the square root of 6 over 2. Okay. So these angles are quite close. The angle between two intersecting planes, we defined it just to be the angle between the normal vectors. Okay, that's how the book defines it. So in this case, the So the cosine of that angle is going, so it's like, here's one and here's the other, and you want to find this angle right here. So the cosine is going to be n1 dot n2 divided by the length of n1 times the length of n2. Okay. Okay. And in this particular example, we see that we have the plane, our original plane, and then 5x plus 3y plus z equals negative 2. We can let n1, so n1 is 1, 1, negative 2, n2 is going to be 5, 3, 1. And we get, this will turn out to be, the dot product is 5 plus 3 minus 2, that's 6. And then divided by the square root of 6, and the square root of, see, 5 plus 9 plus 1 is the square root of 35. Okay. So theta is going to be approximately 65.5 degrees. Just calculate this, take the inverse cosine, and you get this. All right. So there's a lot of stuff we did in this lecture, okay? And but again, all of these, draw a picture. A picture is worth 1,000 words, and the more practice you get with this, the better you'll be. So that's all for today. Thanks.